Okay, so here is the retest tutorial. So remember, you have to watch all the video, answer the question afterwards. If you miss the question, you have to write it on that separate sheet of paper that I gave you. Okay, so let's start with the beginning. Write the complete electron configuration. So this will be number 1, so both of them. All right, so we have SI. If we look on the periodic table, where's SI? It is right here, number 14. So we have to do the electron configuration until we get to SI. So we start with 1s2. After the 1s2 comes the 2s2, then the 2p6, then the 3s2, and then silicon, which is right here, 3p12, so 3p2. And there we go. Next, I have iron with a +3 charge. So if I'm doing this, we're going to try to do iron first and then change it to get rid of 3 electrons because it has that +3. So iron, that's all the way in the d orbital. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. And if I'm looking at iron, it is 1, 2, 3, 4, 5, 6. So 3d6, just like that. And then now I need to take away 3 electrons. Remember, when I'm taking away electrons, I have to take it from the furthest away from the nucleus. So my 4s orbital is going to lose electrons first. There's 2 electrons, and I need to lose 1 more, so I'm going to take it away from the 3d orbital, and now I have 3d5. And so there's the electron configuration. Okay. The second part, number 2, is the shorthand configuration. So remember, this is the one with the noble gases. You have to know your noble gases before you can start moving on. So here I have thorium, TH, which is all the way at the bottom down here. If you look down here, TH, there it is. So I have to go to the noble gas before TH. This is number 90, 89, 88, 87, and 86 right there, Rn. So in brackets, Rn. And then just go to thorium. So after Rn comes these two, 7s2, 6d1, 5f1. So 7s2, 6d1, 5f1. And there's my electron configuration. Okay, so knowing that I have to do the 6d first, and then I can move on to the 5f. All right, y plus 2. So y is over here. See, number 39. So the noble gas before number 39 is 36, or Kr. So in brackets, I'll put Kr. Okay. After Kr comes 5s2, and then 4d1. So that's Y, but it has a +2 charge, so I have to take away 2 electrons. So if I need to take away these 2 electrons, I'm going to get rid of these 2 because remember, they're the furthest from the nucleus. So there's my electron configuration, my shorthand. Kr, 4d1. Okay, number 3. Which has a greater ionization energy, SC or GA? So let's find SC, which is here, and GA, which is over here. Okay, so they're on the same period. So what is different about SC and GA? GA has more protons. Because since they're on the same energy level, GA has more protons, so GA. Why? Because it has more protons. And since it has more protons with the same number of energy levels, this has to be smaller. So because it has, more protons, it is smaller. And since it is smaller, it is harder to remove electrons. Okay. All right, the next two, RB and NA. RB is here, NA is up here. So this one's going up and down. So if we look, NA is in the 3rd period, whereas RB is in the 5th period. That means NA only has 3 energy levels, whereas RB has 5 energy levels. So, which one has a greater ionization energy? NA. Why? Because it has, less energy levels. If it has less energy levels and less electrons, then it is smaller, so harder to remove electrons. There we go. All right, number 4. Which ion has a charge of +2 and an electron configuration of Ar 4s2, 3d10, 4p6? Okay. So first let's just figure out what element that is. So starting with argon here. There's argon. We have 4s2, 3d10, 4p6. So we're at Kr. Okay, so Kr. It says an ion that has a +2 charge. So when I take away 2 electrons, I'm going to get this electron configuration. Okay. So if I'm looking at my periodic table, when I take away the electrons, it's Kr, then my element has to be Sr then. Because when I take away both of those electrons, it'll be Kr, and this has a +2 charge. So it had to already been something from this column right here. But I know it's Sr because if I take away those 2 electrons, I get 36. So which ion? So this would be a strontium ion. All right. Next, how many valence electrons are in the atom with an electron configuration of 1s2, 2s2, 2p6, 3s2, 4p4? First things first, just figure out what element this is. So looking at my periodic table, 1s2, 2s2, 2p6, 3s2, 3p4, I'm going to get to sulfur. So I know for sure it is sulfur. Okay, just based off of this electron configuration. Then I could do a couple of things. I can add up these 2 right here, because these are my most outer energy level. Or what I could do is I could just look on the periodic table. Sulfur is here. And so if we're counting 1 valence electron, 2, skip the metal, 3, 4, 5, and 6. So sulfur has 6 valence electrons. Number 6. How many unpaired electrons does MO have? And is it para or dimagnetic? Okay, so MO is right here. How many unpaired electrons? First step, write the electron configuration, shorthand, to make it easier. Before MO comes Kr, so we're going to start with Kr and go to MO. So if I'm doing that, it'll be Kr in brackets, then it'll be 5s2, 4d, 1, 2, 3, 4. Okay. So in order to figure out how many unpaired electrons I have, I need to draw out the last one, which is my 4d4. That was the last one I filled in. My d orbitals have 5 separate orbitals inside of there. So here's my 4d. I'm going to draw it out. 1, 2, 3, 4, 5. And I'm going to have 4 electrons in those orbitals. So 1, 2, 3, and 4. So how many unpaired electrons does this have? This has 4 unpaired electrons. And if it has unpaired electrons, it is paramagnetic. There we go. All right, next. Identify the element whose electron configuration is this one. This is a little bit easier. Starting with Xe, because that's my noble gas that I have. Starting with Xe, we're going to do 6s2. So looking over here, 6s2. 5d1, 4f14, go all the way down, and then it says 5d3. So remember, you have to do the 5d1 before you can go to the 4f, but to identify the element, it's going to be 5d1, 2, and 3, and so my element will be Ta. Okay? And so 5d was technically the last one I wrote, so that was the one I look at. My 5d3, 1, 2, 3, Ta. All right, number 8. Identify the element in the PES graph. Okay, so here is my PES graph. I have here my 1s2, 2 electrons, it tells me right there. This one would be my 2s2, 2 electrons. This peak right here goes up to 4, so this should be my 2p4. What element is 2p4? That would be oxygen. So this is oxygen's PES graph. And number 9, they kind of go together. Identify the peak in the graph that represents the 2p orbital. Okay? The only one that represented the 2p orbital would be this one, which is letter C, because there's a little c there. So letter C represents that orbital. Number 10. When light is emitted, what are electrons doing specifically amongst energy levels? Okay, when we're talking about light being emitted, what I'm telling you is that electrons, yes, they do get excited and they move to a higher energy level, but that is not the light that I see. That is the energy that is being added to my electron. So when the electron moves down an energy level, it produces energy or emits light. That's how I see the light, when the electron moves back down the energy level. Okay, next. Here I have a ionization table. So it tells me the first, second, and third, and fourth ionization energy. It also tells me that the element is in the fourth period. So if it is in the fourth period, I should only be looking on any element in here. That's the only place I should be looking, because it's in the fourth period. So looking here, the biggest break I can see from all four of those numbers is right here. And so if that's my break, then I know that this has 2 valence electrons. And since I know it has 2 valence electrons in the fourth period, what has 2 valence electrons? Calcium. So this would be calcium. Next. I don't know what number we're on. Let's see, 12. As wavelength increases, what happens to the frequency and the energy? So this is saying, let's say I have a wavelength like this. If my wavelength increases, meaning my waves are much, much longer, what happens to the frequency? My frequency decreases. Remember, frequency is waves per second. So if my waves are longer, I'm going to have less waves per second. And since I have less waves per second, then my energy will also decrease. Okay, you have to know that relationship. Wavelength is inversely related to frequency and energy are directly related. All right, next. What color on the visible spectrum carries the most energy? Now, some of y'all might have missed this problem because you were just thinking that this was violet, but violet wasn't an answer choice on the table. You need to know all the colors in the order I give it to you. And the way you can remember it is R-O-Y-G-B-I-V, Roy G. Biv. Whereas violet is the most energy, red is the least energy. So I think on your test, I would give you blue or orange, and you needed to know that that was the correct answer based off of your data. So in this problem, which color has the most? Violet. But if we're going in order, you would go backwards if I'm looking for most energy. Have to know every single color. All right, let's get to the math problems. All right, a photon has a frequency of 3.15 times 10 to the 11th hertz. Calculate the energy. Okay, so I have frequency and energy. There's only one equation that has V and E, and that is E equals HV. And so they're looking for energy, so I don't need to change the formula. So it's just H times V. So let's plug in H. There's H times V, so that also goes at the top. Remember, hertz, I always change hertz. I have to change hertz, or seconds negative 1, I always have to change it to 1 over S when I'm plugging it into the equation. So it's H times V times 1, I don't need to write it, but divided by S. And so looking here, my S's will cancel out. I'm left with joules. They want the answer in joules, so we're done. We just need to plug it in. So here we go. So 6.636 e to the negative 34th times 3.15 e to the 11th. And I got 2.09 times 10 to the negative 22 joules. Okay. Moving on. A photon of light has a wavelength of 5.25 times 10 to the negative 4 millimeters. Calculate the energy. Okay, so this has energy in it, and this has wavelength. There's only one equation that has both of those. E equals hc over wavelength. I'm solving for energy, so I don't need to change the formula, so this is it. So plugging it in, H just comes first. 6 times 10 to the negative 34 joules times seconds. Times C, so I'm going to put C, 2.998 times 10 to the 8th meters divided by seconds. Divided by the wavelength, and the wavelength goes right here. 5.25 times 10 to the negative 4 millimeters. Good so far. Let's cancel out. Seconds, and that's it. They want me to calculate the energy, so basically they want their answer in joules. So that's the only thing I want to keep. I want to keep this joules. So I need to get rid of meters and millimeters. I need to get rid of both of them. So we're going to do a metric conversion. Millimeters, meters. 1 meter is 1,000 millimeters. And there we go. Just plugging it in. I have, what is it, 6.626 e to the negative 34 times 2.998 e to the 8th divided by 5.25 e to the negative 4 times 1,000. And in 3 significant figures, my answer is 3.78 times 10 to the negative 19 joules. What?
You don't have my push tube, do you?
No.
Okay. Couldn't find it earlier.
All right. And next, I have a photon has a frequency of 3.90 times 10 to the 13 hertz. What is the wavelength of this photon? And so here I have frequency and wavelength. And so what equation has both of those? C equals wavelength times frequency. Okay. So to calculate this one, this time they're looking for wavelength, which is this one on the left. So to do that, remember, I divide by V. V will cancel out, so C divided by V is equal to my wavelength. And so that's the equation I use. C divided by V. C is 2.998 times 10 to the 8th meters divided by seconds. Divided by V, 3.90 times 10 to the 13 hertz. Remember when we change hertz to 1 over seconds. So I put seconds up here. Seconds cancels out. They don't ask specifically what they want wavelength in, so I just calculate it. This divided by this, and that's my answer. And so my final unit will be meters, because that's all that's left. If they ask for millimeters, I would have to do another step. And so 2.998 e to the 8th divided by 3.90 e to the 13. And my wavelength, 7.69 times 10 to the negative 6 meters. All right, last problem. If a sample releases a photon that has a wavelength of 4.11 times 10 to the negative 11 meters, what is the energy in kilojoules per mole? So this was the one that you had multiple steps in. So we have wavelength and energy. So there's only one equation that we have. E equals hc over wavelength. I don't need to change the formula because they're looking for energy, so I can keep it like this. H times C divided by wavelength. H times C divided by the wavelength. Cancel out what I can cancel out. Meters and seconds. So I'm just left with joules. All right, this has an extra step to it because they want this specifically, kilojoules divided by moles. So I have joules. I first have to change it to kilojoules because that's what they want at the top. So joules here, kilojoules. 1 kilojoule is 1,000 joules. And joules will cancel out now. Okay, good. We're good so far. Now we have kilojoules at the top. They also want mole at the bottom. So I need to put mole at the bottom. Mole. Remember, whenever we're doing a conversion with mole, we're talking about photons individually. This is a photon of light specifically. So I'm going to change photons to moles. 1 mole is equal to Avogadro's number. And that will give me mole at the bottom, or kilojoules per mole. Putting this into the calculator. Oops. And I got this, which is 2910596, but I need it in 3 significant figures, so I'm just going to put it in scientific notation. So here's my decimal: 1, 2, 3, 4, 5, 6. So 2.91 times 10 to the 6 kilojoules per mole. And there's the answer.